Wow, it's really hot here at the
So
beach.
hot, I'm
Gosh,
sunburned.
I'm red. We got to,
Yeah.
oh man,
Yeah,
how about a
here,
bit
here,
of water?
here's
Oh, water. Hey, you got some water. That's good. Oh, we're going to have to go into one of the beach huts to finish this example
Let's
at the
do that.
beach.
Okay,
yeah,
let's go.
Let's go to the beach hut. Well, we made it into the beach hut here
Yeah,
with this
yeah.
light board. Isn't that nice? They have a light
Yeah,
board at the
they have
beach.
it everywhere. Yeah.
Everywhere you go, you can find a light board. So we're going to do example counting wave crests in 2D at the beach because
Sounds
we're
good
at
to
the
me.
beach house. So here's a graph, and we have
Yeah, we were watching the waves, right?
watching the waves. So here's the wave crests coming in. This is a line. These are all wave crests coming in. It's like a plane flying over. So the water's here, the sand is here, and of course we need some coordinates, x and z. So lambda is a wavelength, the distance between crests as the waves coming in. But now things are in 2 dimensions, whereas before lambda was in 1 dimension.
Yep.
So we need an x counting crests horizontally.
Sure. So I guess I'll put in lambda x here.
Lambda x here. How about z?
Let's do that too.
Lambda z. Right. All right. So geometry here. Sam, what's lambda x?
Well, we have theta here. Sine of theta is just going to be lambda over lambda x. So you swap them,
Swap them.
and you have lambda divided by sine theta.
Lambda over sine theta. And how about lambda z?
Very similar as last time, just divide by cos theta.
Oh, now we know these are like effectively in 1 dimension. So we're looking at crests, counting crests horizontally.
Yeah, one way or the other.
So that means we can easily count the wave number 1D along the x direction. So now just thinking of 1D, what's this has to equal?
What this has to equal? Just 2 pi over lambda x.
2 pi over lambda x, which is equal to 2 pi. You put this in, the sine theta comes upstairs. Sine theta over lambda.
Looks good to me.
Yeah, and kz same except with cos.
With cos.
Wow, I think we're going to get an interesting result here. Now, we want to find the magnitude of k, which is equal to?
So the sum of squares and then square root again.
Hey, I think we're going to get something what we anticipated in the previous video.
Something very similar to what we almost did.
But remember, when we did it, we didn't have the sines and cosines in there.
Cos theta.
All squared, which is?
Oh, well, you can factor out, and then that's 1. And oh, it's just 2 pi over lambda.
Which is what we said previously. So
That's beautiful.
So we've counted the wave crests correctly, and it all makes sense because we know what the magnitude of k is in the direction the wave's moving is just 2 pi over lambda. Well, here's something interesting is we now can count wave crests in the x direction. We have all the math here, and often in optics we have an incident wave and a reflected wave and a transmitted wave, and those waves are all going to be glued together, and there's going to be a condition in the k horizontal for all those. It has to be the same because a wave is moving on the boundary at the same speed, whether it's reflection, transmission, or incident. And so we can use this in optics, and the fact that this kx, lambda x, is the same for all waves gives us Snell's law.
Wow. Matt, only you can relate a beach to
Snell's law.
To Snell's law.
Yeah, well, we all like going to the beach, and forward on to Snell's law.
Well, now that my sunburn's gone, maybe we can go back out.
Yeah, that's a good idea.
Yep.